Okay, so in the previous video we talked about how to solve an absolute value equation. Now we're going to talk about how to graph an absolute value function. And we're also going to talk about how to graph this idea called a piecewise linear function, which might seem scary, but really isn't too bad, so don't be frightened by it. So the standard form for an absolute value function will be this. F of x equals a absolute value of x minus h plus k, where the vertex point of the absolute value is hk, because the absolute value will make either a v. Either a normal v if the a is positive, or an upside down v if the a is negative. Where the slope of those two lines is based off a, where it will be if a is like 4, one line will be 4, the other line will be negative 4. If a is like a negative 2/3, one is negative 2/3, the other one is positive 2/3. So this equation right here, the idea behind graphing it is to find the vertex point, which is given to us directly in the equation, plot the points, use the slope of a, the number in front of the absolute value, to plot the next 2 points. Make sure you recognize that if the a is 1 or negative 1, it won't show up in the problem. It will just be like no number there or just a negative sign. That tells you your slope is 1 or negative 1 in that case. Then you connect the points to make the v. If we are dealing with inequality, which we will, you still apply these 3 rules to find the points. Just to make sure you connect the v with either a solid or a dashed line, similar to what we did with graphing linear inequalities, and then shade as well, again, similar to what we did with graphing linear inequalities. So if we want to plot this absolute value function right here, we have f of x equals 1/2 absolute value of x plus 4 minus 2. So our vertex point, the x-coordinate of the vertex is always the opposite sign inside the equation. Whether it's positive or negative, it's the opposite sign. Since it's plus 4, we use minus 4. Whereas the y-coordinate is always the same number, negative 2. So we plot that point first. So we go to negative 4, negative 2. And there's our vertex point. Now, because the number in front of the absolute value is positive, we're going to go upwards. And since the slope is a half, we go up 1 to the right 2. And also go up 1 to the left 2, because the absolute value must be a symmetric v. Now we just simply connect the points to create the v of our absolute value equation. And that's all we have to do. Plot the vertex point, and then use the number in front to represent the slope to then connect to make the next 2 points to make our v. Make sure you remember how we're doing this, because this is going to be very similar to when we talk about graphing quadratic functions that are in vertex form. So for a problem like this, same idea. Our vertex point is always the opposite for the x, so it's positive 5. Same for the y, so it's a 1. So we go x is 5, y is 1. Our slope is negative 3, so now we're going down, so we'll go down 3 and then left and right 1 to create our v. So again, we go up or down based on whether it's positive or negative for that a value, the number in front, and we always go left or right the same value. If there's no fraction, we go left and right 1. When there was a fraction, that's why we went left or right 2. So that's our absolute value functions. Now, if it's inequality, same idea. We find our vertex point. Opposite of the x, negative 1. Same for the y, negative 3. Our a value is 2. Since it's positive, we'll go up 2. And we'll go left and right 1. With those other points. Now from here, we apply the rules for graphing inequalities from the linear functions. Since it's just less than, we used a dashed line. And we also apply the same rule for the linear inequalities about whether we're going above or below. Since it's less than, we always go below the dotted lines. So in this case, below the dotted lines is on the outside of the function. That may not always be the case. Below might happen to be inside the v. So never go, it's like, okay, less than means we're outside the v, greater than means we're inside, not necessarily. It just simply means less than we go below the lines, greater than we go above the lines. This will be a perfect example of that. So f of x is at greater than or equal to the negative 2/3 absolute value of x minus 2 minus 5. So again, vertex point, opposite x, same y, 2, negative 5. Our slope is a negative 2/3, so we know we're going down 2, and then we go left and right 3. Now to create the v, because it's equal to, we'll do a solid line. And since it's greater than, we need to be above our v, which means all this region up in here is all above the v. So that'd be the correct shade region there. So again, it can be inside the v, but that's only if, in this case, it had been less than, then we would have gone inside the v in here. So greater than, we go above, less than, we go below. Okay, so that's our absolute value functions. Now the piecewise function is one that's defined as 2 or more linear expressions creating the expression itself. For this year, I think we're only going to deal with 2 linear expressions. We're not going to deal with 3 or more. So this is an example of what a piecewise function looks like. F of x is equal to negative x plus 4 if x is less than or equal to negative 3, whereas it's 2x plus 1 if x is greater than negative 3. It's 2 different possibilities based off what our x value is. So when we talk about graphing this, since they're both linear expressions, we need 2 points to create each particular piecewise linear function. The first point for each one of those expressions must be the transition points, where the transition point is this number right here. That's where we transition from the top graph to the bottom graph. So we must plot that point, and we'll use the slope itself to plot the second point. And I'll show you what I mean by this. So f of x equals 2x minus 3 if x is less than 1, x plus 4 if x is greater than or equal to 1. So for the top graph, we plug in 1 for x. So 2 times 1 minus 3, 2 minus 3, negative 1. Now, here's what's important, because technically, the top graph never equals 1, because x has to be less than 1. However, we need to create the shape, so what we're going to do is, when x is 1, y is negative 1, we're going to use an open circle to represent that point. When it's equal to 1, for the bottom graph, we use a closed circle. Now again, we use the idea of slope, since it's a positive 2. We can't go right, because that would go in the wrong direction. We have to keep on going left, so that's why we're going down to left 1. This will give us the correct positive 2 slope. Another alternative, besides using the slope, if you're a little uncomfortable with that in some cases, you can plug in any x value you want that happens to be, that fits the scenario less than 1. So for example, we plugged in 0 for x. 2 times 0 is 0, 0 minus 3 is negative 3, and notice that's where this point is right here. So feel free to do that. So in the bottom graph, we also use x equals 1, so y equal 1 plus 4, which is 5. So for this example, we'll go to 5 for the y, and because we're equal to 1, we will shade in that particular point. Slope is positive 1, so we go up 1, right 1, and there's that graph right there. So this would be the final version of our piecewise function graph. We're using 2 different components to it. We're noticing we have a linear line down here that's based off the 2x minus 3, but only using x values that are less than 1. Whereas this graph up here is using our x plus 4, we're only using x values that are greater than or equal to 1. So theoretically, what you could do is you could always just simply graph both those lines and then erase the excess portions that you don't want. Depending upon the equation, that might be more challenging. You might be better off just simply doing what it suggested here, plugging in the transition point, using full slope to find the second points. Ultimately, it's up to you. If your graph is mathematically correct, I'm not going to comment that you did something differently from me, so don't feel like you can't do that. Whatever you're most comfortable with, because ultimately, you're the one taking the quiz or the test, and you're the one doing it for a grade. Okay. Alright, so for our next example, we have f of x equals to negative 1/2 x plus 5 when x is less than negative 2, and 3x minus 1 when x is bigger than negative 2. So same idea. Our top function, we need to plug in our transition negative 2. So we have negative 1/2 times negative 2 plus 5. We get 1 plus 5, so it's 6. So at negative 2, 6, we're going to have a point. Since it's equal to negative 2, we're going to shade that point in. Now, our slope is a negative 1/2. which since we're going to the left means we need to go up 1 and left 2 for that particular slope. So it's pretty much recognized for the less than portion. Normally we would kind of go down 1, right 2. That's the correct general direction, but we don't want to go bigger. We can't. We have to go less than. That's where we're going up 1, left 2. And on the bottom function, again, we plug in our transition. 3 times negative 2 minus 1. Negative 6 minus 1 is a negative 7. So we're going to go all the way down to negative 7 for the y. Or again, because it's greater than negative 2, not equal to, we have to have an open circle. And here our slope is a positive 3, so we go up 1, 2, 3, and to the right 1. So that'd be the line for that particular graph. Okay, so that's the idea behind graphing a piecewise linear function. It's just a series of plugging in transition points and then going from there. So I'll do one more and then you'll be okay from there. So again, transition point, in this case is negative 3. So negative 2 times negative 3 minus 4. This gives us 6 minus 4, which is 2. So at negative 3, x is negative 3, y is a positive 2. It's an open circle because it's just less than. And since our slope is negative 2, we go up 2, left 1. And there's that line. So then for the bottom one, we again plug in our negative 3. So 3 times negative 3 plus 11, negative 9 plus 11, and we notice we have the same transition point. It's also 2. That will happen sometimes. So all we simply do is we just simply fill in that point we drew earlier, and now we apply the new slope, positive 3, up 3, to the right 1, and there's that graph right there. So it's kind of like an uneven absolute value function. That will happen every now and then where the transition point is shared by both top and bottom functions. Totally okay. Most times, though, they'll be separate like we had in these previous two examples right here. Okay, so that's your absolute value functions and your piecewise functions. So I'll see you for next time with the next concept.